This video introduces implicit differentiation. So far resources then have focused on cases where a function is simply defined. So we mean you can write things like y equals f of x or w equals g of z or similar. That is, there's a single explicit output and a single independent variable. Sometimes, however, the relationship between two variables is not explicit and cannot be solved algebraically. So here's an example. What if you had a function or a curve defined by y plus sine y equals x squared minus cos x plus 1? You can't easily rearrange this into this sort of form, y equals f of x. How then would you find the derivative or the gradient of such a curve? So we're going to use an observation. Dy dx is the gradient of the curve with x on the horizontal axis and y on the vertical axis. So here's an example. You can see the blue curve and you can see y equals f of x. And if you want, you can work out the gradient at a specific point. The arrow's been in the wrong place, but here you can see the gradient is 470. A simple swapping of the axis reveals that the gradient is of course now the inverse. So if I write x equals f to the minus 1 of y, which means you have the inverse function, and here you'll see I've now got y on the horizontal axis and x on the vertical axis, well clearly the gradient is now 1 over 470. So, if you consider a function written as y equals f of x and assume that the inverse function exists so that we can easily differentiate, so what we're saying is, can we find dx dy using the inverse function? So x is f to the minus 1 of y. Then it's obvious that the gradients of each of these curves are the inverses one of another. As in essence, you've got the same curve, but all you've done is swap the axis. So in other words, this is the key observation. Dy dx equals 1 over dx dy, or the product of the gradients, dy dx times dx dy, is 1. And this is quite a useful observation. And the key thing is that this observation will be true even if a simple inverse function expression does not exist. So here's an example. Simple logarithmic function. Find the derivative of the function y equals log x. And we'll assume log's not in my table, so I don't know how to do it. So I'm going to use the inverse function. So write x as a function of y. And you get x equals e to the y. What I can do now is differentiate with respect to y. So this is different. I'm doing d dy. So what you're going to get is dx dy equals e to the y. Now I can use the inverse to find dy dx. So dy dx is 1 over dx dy, which is 1 over e to the y, which is 1 over x. So you noticed I've got dy dx in terms of x by first differentiating with respect to y. I've used the inverse function. Here's a different example. Find the gradient dy dx of a curve defined with the following expression. So y equals sine to the minus 1 of ax. So again I'm going to do the same trick. I'm going to first use the inverse function. So the inverse function, I can solve that sine y over a is x. So there's my inverse function. And now I can differentiate, and that shouldn't say with respect to x, that should say with respect to y. So I get dx dy equals cos y over a. And then I use the same observation as before, which is that dy dx equals 1 over dx dy. And so you'll see here dy dx is a over cos y. And then I can substitute in a few observations, in essence that cos y is the square root of 1 minus sine squared y, and we already know sine y from this expression up here is ax, and so again with a bit of a rearrangement I can get the expression back in terms of x. What about using the chain rule on y then? Let the expression contain functions of the dependent variable y. And using the chain rule, the following is obvious. So what you'll remember from the previous video on the chain rule is that d dx of f of y is going to be df dy dx. So that's what we're going to be using in the following. So here's an easy example. If you want to do d dx of y squared, then you'll see you get 2y, so that's d dy of y squared, times dy dx. If you want to do d dx of sine y, you get d dy of sine y, which is cos y, and then dy dx. So this is what we're going to be doing in our implicit differentiation. Wherever we have a function of y, we're essentially going to go df, dy, dy, dx. So implicit differentiation, there's two observations that we use. We use the observations that the product of the derivatives dy dx, dx dy is 1, and we use the chain rule. And we might use both, or we might use just one, depending upon the scenario. The key thing is use the easiest. So a good mathematician uses the easiest tool for the problem in hand. So here's an example. Find the gradient of a curve defined with the following expression. So here I'm going to use the chain rule. So I'm going to differentiate every term in the expression using the chain rule for any terms which include a y. So we're going to get the derivative of y with respect to x, dy dx. The derivative of cos 2y with respect to x is going to be minus 2 sine 2y, dy dx, and then obviously the derivative of x cubed plus x with respect to x is 3x squared plus 1. And now all I have to do is separate the variables. So you'll notice I can take out these two dy dx terms, I can separate them out, and I end up with an expression dy dx equals 3x squared plus 1 over 1 minus 2 sine 2y. Now, a key point is don't worry about the fact that this derivative expression includes values of x and y, because so did my original curve. That was how it was expressed, so I expect the derivative to have values of x and y in it. Second example, a circle. Find the gradient of a curve defined with the following expression. Y squared plus x squared equals 4. So exactly as before, I'm just going to differentiate every term in the expression using the chain rule for any terms which include a y. So what do you get? d dx of y squared is 2y dy dx from the chain rule. d dx of x squared is 2x, so I get 2y dy dx plus 2x equals 0. And clearly I can now solve for dy dx as minus x over y. And again, you note that the answer includes values from both x and y. Now it's easy to show that this formula works. So here, if dy dx is minus x over y, and here's an example of a particular point, x and y, and you can see what the gradient is. Example 2. In this particular case, you could have derived an explicit expression for x in terms of y. So y equals the root of x squared minus 4. And I don't really want to get into issues of am I going to take the plus root or the minus root and so on. And hence you could differentiate this and find that dy dx equals x over the square root of x squared minus 4. And then you would find that actually this reduces to the same answer as on the previous page. Another example. Find the gradient dy dx of a curve defined with the following expression. So I've got y squared plus y to the 4 plus cos y equals 4x. So I could use the chain rule. So differentiate every term in the expression using the chain rule for any terms which include a y, and I'll get this. 2y plus 4y cubed minus sine y all times dy dx equals 4, so I can rearrange that and get dy dx is 4 over 2y plus 4y cubed minus sine y. So that's one way of doing it. Alternatively, I could say, look, in this expression, I can easily write everything making x what appears to be the dependent variable. So if I differentiate with respect to y, then this is what I get. d dy of y squared plus y to the 4 plus cos y is 2y plus 4y cubed minus sine y, and then I'm going to get equals 4 dx dy. So here I've differentiated with respect to y rather than with respect to x. And then all I do is recognise my inverse relationship. Dy dx is 1 over dx dy, and I get 4 over 2y plus 4y cubed minus sine y. What about logarithms then? Find the gradient dy dx of a curve defined with the following expression. And here, what I'm going to do is use the inverse function. So first express using the inverse function or using exponentials. So I get e to the y equals x squared plus 3x minus 1. So now I'm going to differentiate every term with respect to x using the chain rule where required. So I get e to the y dy dx equals 2x plus 3, or dy dx equals 2x plus 3 over e to the y. I can then substitute in for e to the y from here, and I get dy dx is 2x plus 3 over x squared plus 3x minus 1. Now, I'm going to generalize this on the next page so you can see a general rule which may appear in your tables. What if I had y equals log of f of x, where f is at this point not defined? Then all I do is again use my exponentials, so I write e to the y equals f of x. I now differentiate with respect to x using my chain rule, so e to the y dy dx equals df dx, or dy dx is 2x plus 3 over e to the y, and of course you'll notice that e to the y is just f of x, so you get this term here. Dy dx is df dx over f of x, and that is a very well-known formula. If you differentiate log of f of x, you get the derivative in the numerator and the original f of x in the denominator. So a summary. This brief resource has derived the rule for implicit differentiation, and this is needed when the output or dependent variable is not defined explicitly in terms of the independent variable, and it can also be useful for inverse functions. The basic method is to differentiate every term in the expression using the chain rule as required, and then separate out the terms which include the derivative. At times, you'll find it useful to recognize that dy dx times dx dy equals 1.